So this video is an introduction to integer partitions and the Rogers-Ramanujan identities. So typically what an integer partition is, it's a way of expressing a natural number as a sum of smaller natural numbers where ordering doesn't matter. Since ordering doesn't matter, what we'll do is we'll fix an ordering. So we'll use a weakly decreasing ordering. So let's start with the definition. So I'll say let n be a natural number. A partition of n is a sequence of natural numbers. Let's say a sequence, let's say lambda 1, lambda 2, through lambda k and n, satisfying the following. So such that, again, the one condition that we want is lambda 1 plus lambda 2 plus dot 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 plus lambda k is equal to n. We want to make sure these numbers add up to n, but we also want to somehow capture the fact that order doesn't matter. So if I write 8 as 5 plus 3 and 3 plus 5, that'll be counted as the same partition. So what we'll do is we'll impose a weakly decreasing restriction on our parts. So we'll say lambda 1 is greater than or equal to lambda 2 is greater than or equal to dot 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 is greater than or equal to lambda k. So for example, if I want to partition 8, I'll just write 5 plus 3. We call the lambda i's, so we call the lambda i's the parts of the partition. So these guys will be known as the parts. We have a function, so we denote by p of n the number of partitions of n. So this, p of 5 will tell me how many ways I can partition 5, and we'll do that as an example in a second. And we set p of 0 equal to 1 for convenience. We just say 0 has the empty partition, so we'll count that as one partition in this case. We often use the notation, so we'll often write, so we'll call the partition lambda, and we'll write lambda as a tuple, lambda 1 comma lambda 2 up to lambda k. So oftentimes when we write a partition, we'll write it this way. And moreover, if one of the lambda i's repeats a few times, sometimes we'll write it with an exponent. So if lambda I, let's say, repeats a times, we'll often write lambda I to the a in our partition. So let's maybe look at a few examples of this notation. So our first example will be, let's say the partition 5 plus 5 plus 5 plus 3 plus 3 plus 1. So this is a partition. And there are a number of ways we'll write this. So we'll sometimes write this as lambda is equal to 5, 5, 5, 3, 3, 1. And this is a little bit inconvenient because we have to write the 5 a bunch of times. So a lot of times we'll substitute, or we'll use the shorthand rather, 5 cubed, 3 squared, 1 to the 1 for our partition. So this indicates that we have 3 5s, 2 3s, and 1 1 in our partition. Let's maybe look at another example. We can ask the question of how many partitions does 5 have? So how many partitions does 5 have? So in other words, i.e., what is p of 5? All right, this is a natural question to ask. How many ways can I break 5 up into a sum of smaller natural numbers? And the one thing that I'll notice is, well, right now the only way I have of doing this is just writing down all the partitions. So I could write 5, I could write 4 plus 1, I can write 3 plus 1 plus 1, I can write 3 plus 2, I can write 2 plus 2 plus 1, I can write 2 plus 1 plus 1 plus 1, or I could just write 1 5 times. So 1 plus 1 plus 1 plus 1 plus 1. And then I can take a look and see, well, how many partitions does 5 have? We have 1, 2, 3, 4, 5, 6, 7. So we would say p of 5 is equal to 7. These are the 7 ways of partitioning 5. So this is just a simple example. a lot of times 4 plus 1, for example, can be written as 4 comma 1. 2 plus 1 plus 1 plus 1, we'll often just write as 2 comma 1 cubed, or 1 to the 3 to indicate that there are 3 ones in our list. Okay, so these are some basic examples with partitions. And so one might ask, well, how do you study partitions? There are primarily 2 ways of studying partitions. One way to study partitions is the use of what are called Young diagrams. So what is a Young diagram? Basically, what we do is we represent the partition as a series of dots, right? So what I'm going to do is I'm going to say each row in this diagram represents a part. So each row in the diagram represents a part. So for example, if I want to represent the partition 2 plus 2 plus 1, what I'm going to do is write 2 dots in the first row, 2 dots in the second row, and 1 dot in the third row. And this is the partition lambda is equal to 2 to the 2 comma 1. That's what I'm representing here. If I want to represent the partition 5 plus 3 plus 1, right? So this is the partition lambda is equal to 5 comma 3 comma 1. What I do is I write 5 dots in the first row, 3 dots in the second row, and 1 dot in the third row. So this is one way of representing partitions. And then using various transformations, one can study different types of partitions. So using different transformations of these diagrams. One very common operation with partitions is actually the idea of conjugation. So what is conjugation? What we'll do when we conjugate partitions is we write the rows as columns, essentially. So think of this as taking like the transpose of a matrix or something like that. So we write the rows of our diagram, of our Young diagram, as columns. So for example, if I take the partition from above, this partition 5 plus 3 plus 1, so this is 1, 2, 3, 4, 5 dots, 1, 2, 3 dots, 1. What I'm going to do is, so this is lambda's 5, 3, 1. What I'm going to do is I'm going to form the conjugate partition, so lambda bar. And the way I'm going to form this conjugate partition is I'm going to write the first row of 5 dots in lambda as a first column of 5 dots. So 1, 2, 3, 4, 5. Then I'm going to take the second row and write it as a second column of 3 dots. And then I'll take the last row of 1 dot and write it as a column of 1 dot. So we see that the conjugate partition, we're going to call it lambda bar in this case. What is the new partition? It's 3, 2 to the 2, 1 to the 2. So this is our conjugate partition. This is our lambda bar. And from using conjugation, we can write down a really nice theorem right away about partitions, right? So we'll start with our first theorem, and it basically just uses the fact that this transformation is 1 to 1 and on to. So here's our very first theorem. It says that the number of partitions of n, number of partitions of n with parts less than or equal to k is equal to the number of partitions of n into at most k parts. Okay, so if we think about what this condition means, the first condition is saying, okay, we're looking at partitions and we only want to talk about partitions of n with parts less than or equal to k. So that means we have at most k columns in our partition or in our Young diagram. And the second is telling us the number of partitions of n into at most k parts. This is telling me I have at most k rows. So one thing you might notice is that conjugation moves us between these 2 types of partitions. So first, I'll note that if lambda has largest part j, then lambda bar has j parts. right? Because the columns become rows, the rows become columns. Then the map that sends lambda to lambda bar is a one-to-one correspondence between the two types of partitions, is a one-to-one correspondence between the two types of partitions. So that'll finish our proof. So now we have this one-to-one correspondence, and we'll use this a little bit later on. We'll use this fact a little bit later on. The way we're going to study partitions, though, will not typically involve Young diagrams. Another way of studying partitions is through the use of what are called generating functions, and we're going to focus on the generating function approach. So I'd like to introduce the idea of generating function. So what is a generating function? So a generating function is basically just a way of encoding a sequence as coefficients of a power series of some sort. So we'll say a generating function is a formal power series. So we'll just assume our variables are formal variables. So we're not going to assume they're real or complex valued or anything like that. So it's a formal power series of the form sum a sub n, q to the n. Q will be our variable as n goes from 0 to infinity. And so the sequence we're encoding is a0, a1, a2, so on and so forth. There's one interpretation we're going to make. So we're going to interpret, anytime we see a 1 over 1 minus q, we'll just interpret this as our geometric series. So this is going to be the sum of q to the n, where n goes from 0 to infinity. And if we write out the terms, this is just 1 plus q squared plus q cubed, so on and so forth. So our very first theorem will actually give us a really nice expression for computing P of n. Again, this is not an efficient way of computing P of n, but it's quite a nice result. So our very first theorem with generating functions will be that the sum of P of n, q to the n goes from 0 to infinity, is equal to the infinite product 1 over 1 minus q to the n as n goes from 1 to infinity. And just to kind of clarify what this infinite product looks like, this is saying 1 over 1 minus q times 1 over 1 minus q squared times 1 over 1 minus q cubed, so on and so forth. So this is just going to be an infinite product. So let's prove this very first theorem, right? So let's prove our very first theorem using generating functions. Okay, so let's begin this proof by writing out the infinite product on the right-hand side. So I'll write the product of 1 over 1 minus q to the n, where n goes from 1 to infinity. And what I'm going to do is I'm just going to use our expansion convention. So we'll write 1 over 1 minus q to the n as 1 plus q to the n plus q to the 2n, which I'll write as n plus n, plus q to the 3n, which I'll write as n plus n plus n, so on and so forth. And so if we expand this out, what am I actually looking at? I'm really looking at, well, for n equal to 1, it's 1 plus q to the 1 plus q squared, which I'll write as 1 plus 1, so on and so forth. For n equal to 2, it's 1 plus q squared plus q to the 2 plus 2, so on and so forth. For n equal to 3, it's 1 plus q cubed plus q to the 3 plus 3, so on and so forth. And we just keep going forever, right? N goes from 1 to infinity. And what I'm going to do is I'm going to write this as an infinite sum. So let's write out this expression. This is going to be k bigger than or equal to 0, and sum of a1 greater than or equal to 0, a2 bigger than or equal to 0, all the way up to ak bigger than or equal to 0. And this is going to be q to the a1 times 1 plus a2 times 2 plus dot 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 plus ak times k. And in essence, what we're doing is we're saying, okay, what is one of these summands supposed to represent? It's supposed to represent, well, it's a power of q that I formed using a1 ones, a2 twos, a3 threes, so on and so forth until I've used ak k's, and the largest exponent I've used to form it is k. The one thing that I might notice is that this exponent is nothing more than a partition, right? So notice that the exponent is just the partition what does the partition look like? It's k to the ak. So there are 8k copies of k. K minus 1 to the a sub k minus 1 up till 1 to the a1. All right, so there are a1 copies of 1. And one thing I might notice is that every partition of n appears as an exponent of q. So, and every partition of n, where n is just some natural number, appears as an exponent of q. Right? And the one thing I might notice is, well, how many ways do I then have of forming q to the n? Well, since the ways of forming q to the n correspond to the number of partitions of n, so this tells me that, so that is the number of occurrences of q to the n is p of n, right? So I'm allowed to now conclude, so I can say hence the product of 1 over 1 minus q to the n goes from 1 to infinity, is nothing more than the sum of p of n, q to the n goes from 0 to infinity. Okay, and in case this is a little bit abstract, let's kind of do an example of what exactly is going on, right? In case this proof is a little bit abstract. So let's focus on capital N is equal to 5, for example. So let's maybe do an example of what the heck is actually going on. So what I'm going to do is I'm going to write out my expression. I'm going to start with this product, n goes from 1 to infinity of 1 over 1 minus q to the n. And we already saw that this can be written as 1 plus q to the 1 plus q to the 1 plus 1 plus dot dot dot. 1 plus q squared plus q to the 2 plus 2 plus dot dot dot. 1 plus q cubed, q to the 3 plus 3 plus dot dot dot, and so on and so forth, right? And this goes on infinitely. So I could ask myself, how many ways can I form? Let's say I want to find what's the coefficient of q to the 5. So what is the coefficient of q to the 5? So in other words, i.e., how many ways can I form q to the 5? So how many ways can I form q to the 5? So let's think about it. Well, one way I can do it is do 1 times 1 times 1 times 1 times q to the 5, which is going to appear somewhere later on in our product above, and then times 1 times 1 times 1, so on and so forth. So I can do q to the 5, or I can do 1 times 1, sorry, I can do 1 times q, q to the 1 times 1 times 1 times q to the 4 times 1 times 1 times 1. So I can do q to the 4 times q to the 1. How else can I form q to the 5? I can do q to the 1 times q to the 2 plus 2, right? So I could do q to the 1 times q to the 2 plus 2 times 1 times 1 times 1 times 1 forever. I can do q to the 1 plus 1 plus 1, q to the 2, right? So in the first part of the product, I could look at q to the 1 plus 1 plus 1. In the second part, I could do q squared and then multiply by 1 all the way down. I can just do q to the 1 plus 1 plus 1 plus 1 plus 1, and then times 1 times 1 times 1, so on and so forth. I can do 1 times q squared times q cubed, times 1 times 1 times 1, so on and so forth. Or I can do q to the 1 plus 1, q cubed, and multiply, and the other products are all just 1. So I do q to the 1 plus 1 times q cubed times 1 times 1 times 1 times 1. And the one thing I notice is that these are the only ways I can form q to the 5th, right? So using the exponents that are written down there, these are the only ways I could form q to the 5th. And the thing that I might notice is that all of the partitions of 5 appear, right? The first partition is 5, the next one is 4 plus 1, then I have my 2 plus 2 plus 1, then I have my 2 plus 1 plus 1 plus 1, then I have my 5 ones, then I have my 3 plus 2, and then I have my 3 plus 1 plus 1. So the coefficient of q to the 5 is p of 5, which is 7. Right. So this is just kind of an example to explain basically what the proof is doing. So we can do this for any exponent. 5 seems to be kind of like this nice exponent we can use. just because it's big and it's kind of not too big and not too small. Okay, so these are this is one way of counting integer partitions. We could write out this generating function. There are other generating functions that we'll be interested in, right? Sometimes we're not interested in all partitions of n. Sometimes we want to study partitions of n where the parts satisfy certain conditions, right? So let's maybe look at some other generating functions. So let's say some other generating functions. And maybe we're interested in partitions of n into odd parts. So we'll call this PO of n. This will be the number of partitions of n into odd parts, right? So if I want to look at an example, PO of 5 is going to be 3, because how many ways can I partition 5 into only odd parts? Well, I could write 5, I could write 3 plus 1 plus 1, and I could write 1 plus 1 plus 1 plus 1 plus 1, right? All the other partitions we wrote down for 5 have even parts. They have 2s or 4s in them. So this is how many ways I could write down 5 and break it up into odd parts. Okay, so we might be interested in, well, what about a generating function for PO of n? And we might look at our earlier example, and I might notice that 1 over 1 minus q contributes only 1s to my partitions. 1 over 1 minus q squared contributes only 2s to my partitions. 1 over 1 minus q cubed contributes only 3s to my partition. So one thing I might do is try to eliminate any of those terms that contribute even parts, right? So one of the generating functions I could write down, if I want to write down a generating function for PO of n, q to the n goes from 0 to infinity, I could just exclude the even parts. So I'll just write this as 1 over 1 minus q to the 2n plus 1, where n goes from 0 to infinity. Notice I've excluded the 2's because I've removed 1 over 1 minus q squared. I've excluded 4 as a possible part because I've removed 1 over 1 minus q to the 4th, so on and so forth. So this is 1 over 1 minus q, 1 over 1 minus q cubed, 1 over 1 minus q to the 5th, so on and so forth. Right, so this is PO of n, we'll call this function. So this is partitions of n into odd parts. What if I want to partition n into distinct parts? What if I don't want parts to repeat? So what I'll do is I'll define another function. I'll call it PD of n. Maybe I'll write this as lowercase d to make it a little bit nicer. PD of n. And what PD of n is the number of partitions of n into distinct parts. So in the sense that we don't want any part to repeat. Right? So we don't want any partitions like 1 plus 1 plus 3. Right? That's a partition where the parts aren't distinct because the ones repeat. So how do I write a generating function for PD of n? Well, one thing I might notice is when I write my expression, right, when I write my generating function, the 1 over 1 minus q is 1 plus q to the 1 plus q to the 1 plus 1 plus q to the 1 plus 1 plus 1. And so anything that occurs after q to the 1 is really contributing multiple copies of 1. And the same thing holds for 1 over 1 minus q squared, 1 over 1 minus q cubed, so on and so forth. So another thing I can do is I could say, okay, well, if I only want to include at most 1, 1, I'll write 1 plus q to the 1, right? I'm not going to include the q to the 1 plus 1 because that would introduce 2 1s into my partition. 1 plus q squared, that restricts how many 2's can appear. 1 plus q cubed, that's going to restrict how many 3's can appear, so on and so forth. And the thing I might notice is that this is the product 1 plus q to the n, where n goes from 1 to infinity. So this is our generating function for PD of n. I might be interested in generating function for the number of partitions of n into parts less than or equal to k. Maybe I want to restrict how large the largest part is allowed to be. So I can introduce, let's say, p less than or equal to k of n. And I'll say that this is the number of partitions of n into parts that have size less than or equal to k. So I'm restricting how big the largest part can be. So let's write down the generating function for this. So this is going to be n greater than or equal to 0, pk of n, q to the n. And what is this going to be? Well, 1 over 1 minus q, this contributes ones to my partition. 1 over 1 minus q squared, this contributes 2 to my partition. 1 over 1 minus q to the k, this is going to contribute k's to my partition, and I don't want to go larger than k. I want to make sure all my parts are less than or equal to k. So I can just write this as the product of 1 over 1 minus q to the n, where n goes from 1 to k, or just simply express this as 1 over 1 minus q squared, 1 minus q to the k. I could just simply express it this way. So this is the generating function of the number of partitions of n into parts that are less than or equal to k. And if you remember our earlier theorem using our diagram, this is the same, like the number of partitions here is the same as the number of partitions of n into less than or equal to k parts, right? So this is also equal to the number of partitions of n into at most k parts, less than or equal to k parts. Okay, so these are just some generating functions. We'll be using these quite a bit when we study partitions, namely this p less than or equal to k of n will come up a little bit later on for us. But what I'd like to do is to kind of show the power of generating functions, because one thing that might be that's kind of interesting to observe is that actually, if I look at my two generating functions up here, this pd of n and po of n, if I start writing lists of numbers, I might notice that pd of n and po of n are always the same, right? So pd of 5 is the same as po of 5. Pd of 10 is the same as po of 10. No matter what n I choose, I'll see that they always come out the same. So there's a rather famous theorem of Euler's that we'll prove now. So this is a famous theorem of Euler. And the theorem says for all n and n, so for all natural numbers n, po of n is equal to pd of n. Okay, so the proof is pretty elegant, actually. All right, so the proof is pretty elegant. I'm going to start with the generating function for pd of n. So n goes from 0 to infinity. And I know what this generating function is. This is the product 1 plus q to the n, where n goes from 0 to, or sorry, rather, n goes from 1 to infinity. All right, so it's this product. Now I'm going to do something a little bit clever. I'm going to write this as the product of 1 plus q to the n times 1 minus q to the n divided by 1 minus q to the n. N goes from 1 to infinity. Write the product this way. One thing that I'll notice is that this numerator combines rather nicely. So I'll get 1 minus q to the 2n at the top. And in the denominator, I'll get 1 minus q to the n. N goes from 1 to infinity. Right, so I have a product that looks something like this. And let's kind of expand this out to see what this looks like, because it might give us some indication of what's going on here. So if I were to expand this out, the one thing that I would notice is, well, the numerator, 1 minus q squared, 1 minus q to the 4th, 1 minus q to the 6th, so on and so forth. The denominator is 1 minus q, 1 minus q squared, 1 minus q cubed, 1 minus q to the 4th. The thing that I notice is that the even power terms appear on the top and bottom, and I can cancel them out, right? So what I'm going to do here is I'm going to cancel this 1 minus q squared with this 1 minus q squared. I'm going to cancel this 1 minus q to the 4th with this 1 minus q to the 4th, and so on and so forth. And what are we going to be left over with when we do this? It's going to be the product of 1 over 1 minus q to the 2n plus 1, where n goes from 0 to infinity. Right, so I'm going to be left with only the odd powers of q in the denominator. The whole numerator will cancel out. And what is this the generating function of? This is nothing but the generating function of po of n. Right, q to the n, where n is greater than or equal to 0. Right, so this is Euler's proof of this fact. The thing to notice here is that if the powers of q to the n are equal on both sides, then, or rather, if the coefficients of q to the n are equal on both sides, then we get our theorem. Right, so if two power series are equal, that means the coefficients of each term is the same, right? So the coefficient of q to the n is the same on both sides, which means pd of n is equal to po of n. So this is again Euler's proof of this rather remarkable fact. And in some sense, the Rogers-Ramanujan identities, which we'll get to in a little bit, are some sort of generalization of this, I want to say, or maybe some sort of extension of this. So let's look at some more complicated examples. So I'll start with some other examples. And when we study the Rogers-Ramanujan identities, there are two types of partitions we're going to be interested in. So we'll talk about partitions of n. Let me fix this typo. Partitions of n, where all parts are congruent to 1 or 4 mod 5. And we'll call this P1, 4, 5 of n. This is not a standard notation. This is just a notation that I'll use to indicate what's going on. So I'll put the modulus kind of at the top. And this has a really nice generating function. So P1, 4, n, or sorry, 1, 4, 5 of n, q to the n, where n is greater than or equal to 0. This is equal to, well, if I want to include the parts that are 1 or 4 mod 5, I want to only include parts of the form 5n plus 1 and 5n plus 4. So my generating function is going to be 1 minus q to the 5n plus 1 at the bottom, and 1 minus q to the 5n plus 4 at the bottom, where n is bigger than or equal to 0. So this is a rather simple generating function. The other type of partition we'll be interested in when we study the Rogers-Ramanujan identities are partitions of n, where all parts are congruent to 2 or 3 mod 5. So this is P2, 3, 5 of n. Again, non-standard notation. We're just using it for the sake of this video. So to write down this generating function, this is P2, 3, 5 of n, q to the n. This is the product where n is greater than or equal to 0 of 1 over 1 minus q to the 5n plus 2, 1 minus q to the 5n plus 3. All right, so this will be the generating function for this. And we'll come back to these in a second. These will be kind of interesting for us in a little while. But let's look at some more complicated examples, because right now these are some very simple examples of generating functions. So let's look at one that's a little bit more interesting, where some more counting might be involved. So I'm going to define two functions. I'll say let p sub rr upper 1 of n. So again, this is not a standard notation. This is just a notation I'm making up for this video. This is going to be the number of partitions of n where all parts differ by at least 2. All parts differ by at least 2. So when I talk about these types of partitions, 1 plus 3 plus 5 is such a partition because 1 and 3 differ by 2, 3 and 5 differ by 2, 1 and 5 differ by more than 2. But a partition like 1 plus 2 plus 4 doesn't work because 1 and 2 don't differ by 2. Right? So a partition of this form won't work. Similarly, we can define PRR2 of n. So this has the same condition. So the number of partitions of n where all parts differ by at least 2 right? So this has the same condition, but we're going to introduce one more restriction. I'll say and all parts are greater than 1. So we're not allowed to use ones as our parts. We have to use 2s, 3s, 4s, 5s, so on and so forth. We're not allowed to start with a 1. So these two will play an important role for us in this series of videos. But what I'd like to do is to develop generating function expressions for each of these for each of these functions, these PRR1 of n and PRR2 of n. Right, so I'd like to develop an expression. So our goal is going to be develop an expression for the sum PRR1 of n q to the n. where n is greater than or equal to 0. Right, this is going to be our goal. I'll leave the PRR2 of n as an exercise. The proof will be similar, but it's a good exercise to practice with if you'd like to kind of practice with this material. Okay, so let's develop an expression for PRR1 of n, q to the n. Okay, so what I'm going to do is I'll write this out. So I'll say this is the sum n greater than or equal to 0, PRR1 of n, q to the n. I'll write this as the sum k greater than or equal to 0, and I'll write out the partition. So I'm going to say 0 is less than lambda 1, is less than or equal to lambda 2, is less than or equal to dot, 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 is less than or equal to lambda k. And I'm going to impose the condition that lambda I minus lambda I minus 1 is greater than or equal to 2. So I'll write this as q to the lambda 1 plus lambda 2 plus dot, 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 plus lambda k. All right, so what I'm doing is I'm writing out every single one of these partitions as an exponent of q. I'm writing these in weakly increasing order. Like I said, order doesn't matter. So as long as you fix one order when you're writing this out, that's fine. The one thing to notice is we're imposing this difference 2 condition in our sum. So we're saying lambda I minus 1 is greater than or equal to 2. That's imposing our difference 2 condition. And what do we have? Well, one thing we notice, so we note that for each choice of partition lambda 1, lambda 2, lambda k, let's say of some number n, the thing we notice is that we have, well, the first thing is lambda 1 has to be bigger than or equal to 1, right? Lambda 1 is bigger than 0. Lambda 2, since I have a difference 2 condition, lambda 2 has to be bigger than or equal to 3. Lambda 3 has to be bigger than or equal to 5, and we keep going until we notice that lambda 2k plus 1 has to be, or sorry, rather, lambda k has to be bigger than or equal to 2k plus 1. Right, so this is just coming from the difference 2 condition. So what I'm going to do is I'm going to write the following. So we write mu1 will be lambda 1 minus 1. And we notice that this is bigger than or equal to 0. All right, mu2 is lambda 2 minus 3. This is bigger than or equal to 0. Mu3 will be lambda 3 minus 5. Again, this is now bigger than or equal to 0. And all the way up to mu k, this will be lambda k minus 2k plus 1. Minus 2k plus 1. Okay, so what do we have? Well, given the relationship between the lambdas, this imposes a relationship on the mu's. So we have that mu1, well, it's bigger than or equal to 0, but it's less than or equal to mu2, which is less than or equal to mu3, which is less than or equal to dot, 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 mu k. Right, and what is this a partition of? This is a partition of n, but I've subtracted 1, 3, 5, all the way up to 2k plus 1. So this is a partition of n minus 1, minus 3, minus 5, minus dot, 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 minus 2k plus 1. And the thing that I might notice is that this is just a partition of n minus k squared, right? And what kind of partition do I have? This is a partition of that number into at most k parts, right? Because now the mu's are bigger than or equal to 0. So if zeros occur, we're not going to count them as parts. So this is a partition of n minus k squared into at most k parts. Okay, so what are we looking at here, right? What are we looking at when I go back to my sum? So the thing to recall is that P sub RR1 of n, q to the n, where n is bigger than or equal to 0. We wrote this before in terms of the lambdas, but now what I'm going to do is to convert this in terms of the, to write this in terms of the mu's. So I'll say mu1 is bigger than or equal to 0, is less than or equal to mu2, is less than or equal to dot, 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 mu k. And this is now q to the mu1 plus mu2 plus dot, 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 plus mu k plus 1 plus 3 plus dot, 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 plus 2k plus 1. And the thing that we might notice here is that these numbers, these add up to k squared. All right, so what we're actually looking at is the sum k greater than or equal to 0, sum 0 less than or equal to mu1 less than or equal to mu2, so on and so forth, of q to the k squared times q to the mu1 plus mu2 plus dot 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 plus mu k. Right, so we're actually looking at this expression. And what I'll do is I'll take this q to the k squared and I'll move it out of the sum. I'll write this q to the k squared out here. So the thing to notice now, again, recall this sum with the mu's is now representing the partitions of n minus k squared into at most k parts, right? So we're representing partitions of integers into at most k parts. And we have an expression for that, right? Just a second ago, we saw that the partitions of an integer into at most k parts are given by 1 over 1 minus q squared up to 1 minus q to the k, right? And so we get this rather elegant expression for our generating function. This is going to be q to the k squared over 1 minus q squared up to 1 minus q to the k. All right, so this is k bigger than or equal to 0. All right, so this is a rather elegant expression for our generating function, right? This is kind of what we were after. We're using the fact that we know what the generating function for partitions into at most k parts looks like, right? So this piece that's coming out here, this is the number of partitions of an integer into at most k parts, right? So we're equating it with this guy right here. Okay, and so we get this rather elegant expression. And what's the exercise? The exercise to try, there's a similar expression for PRR2 of n. The exercise, n is bigger than or equal to 0, is that this is the sum of q to the k squared plus k over 1 minus q squared, 1 minus q to the k, where k is bigger than or equal to 0. All right, so we have an expression that looks like this. Okay, so these are more complicated examples of generating functions, but these are generating functions that count partitions with certain conditions. Usually when we want to have conditions that represent like a difference or distance between parts or something like that, the expressions are a bit more complicated, right? So it's kind of the nature of these. So at this point, you might be asking, well, where are the Rogers-Ramanujan identities? Well, the Rogers-Ramanujan identities actually are related to these generating functions. So let's kind of write out what the Rogers-Ramanujan identities are. So the Rogers-Ramanujan identities are the following. The Rogers-Ramanujan identities are the following. The first identity says that the sum of q to the n squared over 1 minus q squared up to 1 minus q to the n, where n is bigger than or equal to 0, is equal to the product, as n is bigger than or equal to 0, of 1 over 1 minus q to the 5n plus 1, 1 minus q to the 5n plus 4. Right? So what this is really saying is this is saying PRR1 of n is equal to P145 of n for all n and n. Right? So the number of ways of breaking up a partition, or rather breaking up an integer into parts that have this difference 2 condition is equal to the number of ways of breaking up that integer where the parts I'm using are all 1 or 4 mod 5. Right? So this is the first Rogers-Ramanujan identity. Then we have the second identity as well. The second identity states that the sum of q to the n squared plus n over 1 minus q squared up to 1 minus q to the n is equal to the product. You could probably guess at this point what this is. It's going to be the other product that we saw just a few minutes ago. 1 minus q to the 5n plus 2, 1 minus q to the 5n plus 3. So this is the second Rogers-Ramanujan identity. And to kind of put this a little bit more concisely, this is essentially the same as just saying PRR2 of n is equal to P235 of n. All right, so using our non-standard notation from earlier. Okay, so I'm going to stop here. In the next video, we'll prove the Jacobi triple product identity. Our goal with the series is to get through the proof of the Rogers-Ramanujan identities, and we want to go through what's specifically called Andrews and Baxter's motivated proof. Okay, so I'll stop here.